Hey everybody, Professor Mankowski here. Welcome to Chapter 1. In Chapter 1, we're going to be talking about an introduction to statistics. We're going to do some preliminary terms and concepts and definitions, what statistics is and what it's all about. Don't worry, you don't need a calculator. We're not going to do any crazy formulas or calculations or anything like that. So if we're in a statistics class, probably a pretty good idea to start by defining statistics. And statistics is the science of collecting studies to organize, collect, summarize, analyze, and draw conclusions from data. Now that's quite a mouthful. You might read that and say, what the heck is that supposed to mean? And what it's trying to say is that statistics is as simple as you want to make it or as complex as you want it to be. It can be as simple as just maybe recording the heights of people in a room. Even if all we're doing is recording somebody's height on a sheet of paper, that's still a statistic. And it can be as complex as using some kind of crazy formula to predict the GDP of the United States for next year. So it can be forecasting also. Now, what it comes down to is the information that you're working with, whether or not it's your opinion or it's fact. And to help us figure out the distinction, statistics branches into two main parts. What we're going to call descriptive statistics and what we're going to call inferential statistics. So descriptive statistics consists of the collection, the organization, the summarization, and the presentation of data. So we're collecting things together, we're organizing numbers, we're summarizing them, and maybe we're presenting them on a sheet of paper or on a projector, a PowerPoint in a meeting. The key aspect, though, is anybody can come in, any third party can validate the information that you're saying and show that it reflects true reality. Our opinion is not in the mix. We're just limiting ourselves to what's factual. Now, if we want to put our opinion in, we can do that. We just have to move to inferential statistics. And inferential statistics happens when we start to generalize, we start to make predictions, we start to forecast, we start to propose that there's a relationship between two different variables. The most important part of inferential statistics is that it's our opinion. It's an educated guess. Even if we have a PhD in statistics or mathematics, at the end of the day, we're still taking a guess about what we're saying. So to help wrap all this up, descriptive statistics is any information that somebody else can come out and validate that is actually true and it happened. Inferential statistics cannot yet be validated because it's somebody else's opinion. So let's take a look at a couple examples of both of these kinds of data. Descriptive statistics could be saying there's, in a classroom, 25 students. So anybody that we bring into the classroom to count up the students is going to end up at the same exact number. We're all using the same numeration system after all, so that would make this a descriptive statistic. Another would be if we took our first test, we counted up how many people got A's, and we said 15 students got A's on the first exam. And we can validate this really easily. We would just need to know that 90% or higher is an A, and anybody we give the stack of tests to and say separate the A's from all the other marks, every time we're going to end up with 15 tests in one pile and the rest in the other. Inferential statistics. If we think back to the 25 students in the class, and we say based on the fact that we have 25 students in our class now, in the same class next year, we're also going to have 25 students, that would become an inferential statistic because we don't know what's going to happen in the future. Let's do another example. If we knew 15 students got A's on the first test, it turns out maybe that 10 of those 15 were women. So now we say it's women that are better at mathematics than men are. Can we say that? Well, sure, we can say whatever we want to say, but the issue is we can't make that statement and consider it valid based on the information that we have at hand. We're making a really big generalization. So that would classify it as an inferential statistic. Okay, so between descriptive statistics and inferential statistics, we know a little bit more about how to describe them and what they look like. Now we're going to talk about populations and samples. In statistics, a population, simply put, consists of all subjects being studied. And the population might be all the people taking Mat 150, or everybody that's a Bergen Community College student, or it could even be all the people in the United States. Now, it doesn't have to be just people. It could also be all the dogs in New Jersey, or all of the striped bass in the Hudson River. So whatever population a researcher is working with, they would have to tell you that at the start of a research project. If we're doing a question about a population, that information has to be disclosed to you at the start of the question. Now, if we wanted to study a population very thoroughly, be very exhaustive, we were working with the American population, people here living in the country. And if we needed to have very conclusive information, would we go and interview maybe every single member of the population if we needed to know people's opinion about some kind of current event that was happening? And we'd probably say, well, that would be nice to do, but how would you know that you got everybody? Like, how could you find every single member of the population? Can we really do this? No, the answer is no, we can't do that. So that's why we have samples. And a sample is a subset of the population. And it's going to turn out that it's cheaper and it's more feasible and efficient to use a sample from a population and then study what we see happening in a sample and then generalize about the population based on what we see happening in the sample. Another reason why we talk about sample and population is because in later chapters, we have to be really careful where our data came from. Was it sourced from a sample or was it sourced from a population? Which one do you think would be more risky to use? Data that came from a sample or data that came from a population? The answer is data that came from a sample. It's going to be riskier because we don't have everybody in the sample that we do in the population. So as we get into our second and our third and our fourth week, we're going to start to learn how to involve error in our forecasts and our estimations based on what kind of a sample we're using. So now we've talked about populations, we've talked about samples. What are the different kinds of data you can end up with in statistics? And we have two major houses, what we call qualitative data and what we call quantitative data. Qualitative data is any information that's not numerical. So just because you're doing statistics doesn't mean that your information has to be a number. It might not be a number. And a good way to remember qualitative data is inside that word, lit appears. And I like to think of that as literature. I think if I go into a bookstore and pull a book off the shelf, maybe a romance novel, is that romance novel going to be filled with numbers and formulas? I mean, besides the page numbers. And we would say, no, it's just going to have sentences and narrative. There won't be any numbers anywhere in it. So that might be something that can help you remember that qualitative is non-numerical information. Now, some examples of that might be somebody's hair color or what kind of car a professor drives. We're not going to work a whole great deal with qualitative data because we can't really do that much with it until we start to code it. And we're not going to get into coding in this statistics class. We're going to spend much more time with quantitative data. So quantitative data is any kind of numerical information, which makes sense if qualitative was not numerical information. So quantitative is going to break down into two pieces, discrete and inferential. Now, discrete is a little bit simpler, so we'll work with that first. Discrete is going to be anything that's a whole number and it's countable. So it needs to meet those two criteria. And if we think of examples of discrete, one example might be a number of golf balls in a bag. Like if we go to the golf course, we can't really go into a golf bag and take out half of a ball, right? We can only have 3 balls or 4 balls. We can't take out 3/4 of a ball to tee off with. It doesn't make any sense. So we can count up the golf balls, but we can't have a fraction of a golf ball. So that helps us understand that golf balls would be discrete. Number of birthday cards you get on your birthday would be a good one. If somebody's sending us a birthday card, we can count up the number of cards we get. And at the same time, we don't really have people that would tear a birthday card in half and mail you half of a birthday card. And if they do, they're probably not going to be your friend for very long. But that would help us identify birthday cards as being discrete data. How many seats an airplane has. If we go into a plane, we can count up the number of seats in the aircraft, And we can easily say 3 seats or 25 seats, but we wouldn't see half a seat in a plane. We wouldn't see 9/10 of a seat in an aircraft. So that's how we could recognize seats in an airplane as discrete level data. So let's go ahead, let's take a look at what continuous would be. Continuous data, this time, is the messy stuff. It's going to include fractions and it's going to include decimals, and in particular, you can't count continuous data, at least not very well. An example might be how much snowfall that we get. Like if you think of a snowstorm coming down, like the snowflakes falling, we can't really look up at the sky and count the snowflakes. That's 1, that's 2, that's 3. It's not going to give us any meaningful information. At the same time, we can get snowfall in a fraction. We could get 3/4 of a foot of snow, 3/4 of an inch of snow. Another example would be volume of water in a pool. If we look at a pool, we can't look at a pool and count up the number of drops of water. It wouldn't make any sense. And we can also get a fraction. Like if we were to measure water in gallons or with liters, we can have half a liter or 1.29 liters. So that would also be an example of continuous data. Now, across continuous data and discrete data, we have different levels of sophistication of how sophisticated your data can get. We have 4 broad scales that we're going to look at: nominal, ordinal, interval, and ratio. And as we go from left to right, we're going to find out that nominal data is the simplest stuff. There's not a whole lot of analysis we can do with it, while ratio is going to be something that's more useful for analysis, and we can do a lot more with it. So let's go ahead, let's take a look at nominal data first. With nominal data, it's going to be information that's comparable and we can categorize it, but the key is you don't have any way of ranking the data values in the data set. Now, what would that stuff look like? A good example might be somebody's phone number. We can go ahead and we can look at a whole bunch of phone numbers. We can say how many phone numbers belong to each area code, but there's no real way of saying one phone number is better than another person's phone number. Most of the time, you just care about getting the digits correct so your phone dials. Nationality is another good one. If we have a whole bunch of people in a room, we might be able to tell you how many people are German, how many people are Spanish, how many people are, let's say, Korean or Australian. We have 4 Germans, 3 Australians, 2 Korean people. But we can't really say anything about the ranking. Like we can't say the Australians are better than the Germans, the New Zealanders are better than the Tahitians. There's just nothing to work with there. So that gives us a pretty good idea of what nominal data would look like. Let's go ahead, let's take a look at ordinal level data. Now, ordinal level data is a little more sophisticated. It's information that we can finally rank. Catch is there's no real precise differences among the data values. And one of my favorite examples to use is hot wings. If you go into happy hour and you ask your server for hot wings, they might say, do you want mild, hot, or inferno? Now, if we have somebody that's sitting down with a pile of inferno wings, the person next to them has mild wings, it's definitely the case that the inferno wings are much more intense than the mild wings, but by exactly how much, like what degree of intensity, we don't really know because we don't have that information. We just know that one is more intense than the other. Another example would be body build. If we think of how you can categorize body build, small, medium, and large. If we have somebody that's large standing right next to somebody that's small, it's pretty obvious that the person who is large is definitely a lot stronger than the small person. But we don't know exactly how much stronger the large person is than the smaller person because we simply don't have that information. Let's take a look at our final 2 categories, interval level data and ratio level data. Now, they share a similarity. In both cases, we have precise differences among our data values. So we can finally say that. The difference, the distinction has to do with something called absolute zero. When we work interval level data, we don't have absolute zero. And absolute zero just means that if you are at absolute zero, you're out of whatever you're measuring. So if interval data has no absolute zero, what that implication is that we can go negative in the data. Now, ratio is the opposite. We have an absolute zero. And if we're at zero, it means we're completely out of what we're measuring. And that scientifically enables us to make ratios out of numbers, where in interval level data, we can't make ratios out of numbers. And we'll see why in just a minute. Let's talk about some examples of interval data. And one of my favorites to use is temperature. Think of two ovens right next to each other. One oven is 200 degrees. The other oven is 400 degrees. Now, if we consider both temperatures, we can definitely say 400 degrees and 200 degrees, there's a precise difference finally. The difference is 200 degrees. And at the same time, there's no absolute zero. That means that when we're at 0 degrees, it doesn't mean we're out of temperature. We can go negative with temperature, can't we? So that's how we classify as interval level data. Now, something really neat that comes up when we're working with temperature, if one oven is 400 degrees, the other oven is 200 degrees, can we say the oven on the right is twice as hot as the oven on the left? It's a deceiving question. We'd like to say 400 is twice as big as 200, so of course we can do this, but that's wrong. We can't. And the reason why is because technically we don't know where temperature started from. Like, we don't know how negative you have to go until you get to the starting point of temperature. We, in theory, don't know how much we would have to take and multiply by 2 because we don't know where we started. And that's enough to prevent us from going and making ratios. A really good example of that would be, imagine that you're going to cook brownies, and the directions call for you to make 400 degrees, cook at 400 degrees for 20 minutes. And we're saying, okay, this is great. Only problem is we don't have 20 minutes, we have 10 minutes. So imagine what would happen if you tried to crank up the heat and go 800 degrees for 10 minutes instead. What is going to happen to your kitchen? The answer is you're going to have a really big mess on your hands. And the reason is we cannot make ratios out of temperatures. That's what's stopping us. So now let's go ahead. Let's talk about the ratio category. We know we have precise differences. We know absolute zeros exist. One good example of ratios would be distance. Think about how far you might drive to your job. If you drive 5 miles, somebody else drives 15 miles, we can get a precise difference between the mileage. 15 minus 5 will give us an exact number. At the same time, we have an absolute zero. If we're at 0 distance, we can't go negative. Like, we don't have any way of expressing a negative distance. So that's how we stay into ratio data. And that's also what gives us the ability to literally make ratios out of numbers. If somebody drove 10 miles, another person drove 30 miles, now we're able to say the person who drove 30 miles drove 3 times as far as the person who drove 10 miles. Bench pressing would be another example of ratio level data. If those of you like to go to the gym, maybe we bench press. If somebody bench pressed 100 pounds, somebody else bench pressed 300 pounds, we would be able to say the exact difference between how much each person bench pressed, and we can also say that the one person who bench pressed 100 pounds compared to 300 pounds, the person that bench pressed 300 pounds did 3 times as much. That works because we're in ratio level data. Obviously, we have precise differences between the bench pressing amounts, and we cannot bench press a negative amount of weight.